So here's, again, a little bit of warm about me. I have some certs. I have a bachelor's in computer science and some of my previous life experience. Just to plug my company real quick, Disruptive Solutions, veteran and employee owned. We work with Carbon Black and Red Canary for endpoint protection and incident response. We kind of specialize in threat simulation, but also SOC training, so we can, impersonate like Fancy Bear or something. Pick a chain of words, and it's probably an APT that we can simulate. So we'll simulate it and give you a really good pen test, and then also train with your SOC to detect and prevent it in the future. So that really helps like financials defend against APTs who are going after financials, and healthcare for defending healthcare from APTs that are going after healthcare. So there's an email address, but you can also reach out to me. I'll put my contact information after if you have any more questions there. All right, we're going to start out with network basics. It's probably going to be really boring if you already know what an IP address is and all that stuff, but here we go. So the very basic form of data on a computer or on a network is a bit, and then you have a nibble, which you probably won't see much at all. But then byte, word, double word, quad. The IP address, MAC address, the amount of bits they have, it's not really important, but it is if you're not looking at it in their normal form. It might help you figure it out. And the white text has already killed me. There's supposed to be an IP address right here in binary, and then the same IP address in decimal, and then the same IP address in hex. So the white text is really helpful. Anyway, there's 8 ones and zeros, and then a dot, and then 8 ones and zeros, and then a dot, and then in decimal, there's the IP address that you've probably normally seen. It's I think it's a 192.168 address, and then hex is basically 0 through F. We'll move on from there, and then there's more text up here that got. Anyway, the OSI model, it's really too far in the weeds for the scope of this talk, but here it is anyway. So you've got, the thing that interfaces with the human is your program, and then your content, session, transport. And what I'm trying to get at here is there's this recurring theme in networking called encapsulation. We're going to talk about it more, but basically the further you get away from the human, like from here down, the more data gets encapsulated or encoded. So the nice, pretty, a web application's not a great example for the OSI model, because the OSI model came after the HTTP. But if your browser's up here, you have your encoded stuff, like so your raw HTML here, and then you have HTTP here that manages your session, and then you have TCP, and then IP, and then So as we go away from the human, we kind of containerize all this data into through encapsulation before we package it and put it on the network. So this is a much more simpler way to look at it, where you have your suite and then your transport, then the internet and your link. So we're going to get into more later, but that's kind of the easiest way to think about the OSI model. So switching and routing are two very important things that happen on the internet or in any network. Switching largely replaced hubs. Hubs were these things where everybody connected into them, but everyone was talking on the same, essentially, wire. So if one person's talking and they're connected to a hub, everybody on the hub receives the same thing. So it was important to develop things like ARP. And ARP translates MAC addresses into IP addresses so that computers can talk directly at the data link layer. Hubs are kind of hubs bring issues into your network because the hub and everyone attached to it is in what's called a collision domain. So what that means is if two computers try to talk at the same time, there's a collision, and then what'll happen is everybody will go quiet for a random amount of time, and then someone will try to talk again. So switching eliminates that problem by basically reducing the collision domain between the switch and each attached node. So instead of having a collision domain of 48, you have a collision domain of 2. Go ahead.
So hubs basically, your network comes in, it's redistributed to everybody else, whereas a switch knows which connection is going to which one, so your stuff comes in and only goes to what it is.
That's right. Yeah, so switches use, like Cisco switches use CEF or CEF, which is Cisco Enhanced Forwarding. Other switches will use something called fast switching. Basically, as the network lives, the switch remembers the MAC address of each node and then builds a forwarding table so that when it sees ARP or when it sees someone looking for a certain MAC address, it knows that MAC address lives off port 23. I'm not even going to burden everyone else with it. I'm only going to look at the destination MAC and ship it. So it's improved speed, it improves reliability, it improves a lot of things. The reason we used hubs historically is because they were cheap. I lost this. I can't hear anything anymore. It rebooted. All right, which one of you did it? We haven't. No, we're back. Yeah. So someone just denial of service to our mixer. All right. So anyway, hubs weren't used largely, or hubs aren't used anymore because the technology of switches has become a lot cheaper, and there's really no point to using hubs anymore. So they're just not made. All right. So routing comes after that, and that's up a layer at the IP layer. So if I needed to, and this is all logical, so switches operate at a physical layer, routing operates at a logical layer, so you can cover much more of an area, I guess, if that makes sense. We're going to get into routing later, but so we'll move on to UDP, TCP, and ICMP. These are just ways that the most common ways that messages are exchanged on the internet or in any network. UDP is used for really fast communications, but it's connectionless. There's no sort of, there's no handshake. So if I just send you a UDP packet, I don't really care if you get it or not. I have no validation to know whether or not you got it. Whereas TCP, there's an established handshake, there's sequence numbers, there's all this built-in technology to figure out if packets arrive in an out-of-order state, it can reassemble them based on the sequence numbers. It can, but it operates. What's that? Yeah, sort of. Yeah, I guess error checks. Yeah, both. I'm pretty sure both packet types have a checksum, so the receiving end of the connection knows whether or not the packet is out of well, not out of sequence, but if it's been corrupted. The sequence numbers would help, like a TCP session, recreate an out of order session. So if you're downloading a file, and let's for some reason say that your file is 4 packets long. If you have a TCP session and packets 2 and 3 arrive before 1 and 4, the receiving end knows which order to recreate the whole thing in. Then ICMP is for control messages. So like when you use traceroute, you're sending UDP out, and then at each further hop, the TTL gets decremented, and if the TTL expires, you get an ICMP back saying time to live exceeded, and it can't go any further. So again, here's kind of a picture for encapsulation. Again, as you start up here with your HTTP and your browser, you go down into TCP, you get you encapsulate into it with a TCP header, and then TCP payload, and then after that you get an IP header, and then everything else is appended to it, and then after that you get your frame header. So if you look here, there's a black line that kind of snakes its way up here. That's more or less the physical path of the actual information, and then these colorful arrows up here to signify logical connections. So what happens with your session is it gets encapsulated on the way down, and then it makes it over here. This is a router, and this is a router, and then this is your endpoint. So it makes it to the first router. The Ethernet frame gets stripped off, and it goes up to the IP layer. The router looks at the IP, decides that it is not the destination IP, and then figures out where to send it to next. In that case, this is router number 2. So it puts a new Ethernet frame on it, encapsulating again, and then ships it on the wire. The same thing happens, and then we get over here. This guy decides that is the destination IP address, so it takes it one step further, strips off the TCP header, and then passes it to the HTTP application, who will then likely process your request. So that's a lot of information with just a picture, but any questions in this picture? No, all right. So here's another way to look at encapsulation is boxes, and then this nice picture down here. I guess I chose this picture because it shows that it's the frame is the only one that really gets a footer, which is kind of interesting that UDP doesn't really have it, TCP doesn't have it, IP doesn't have it, so there's no pointer to the end. It stops when it stops. So I think that's enough for encapsulation. I'm really sorry that I'm showing you hex on a presentation, but we've got this is what the packet looks like. So the first set of dotted lines up here at the top is your frame header. So the red is your destination MAC address, source MAC address. 0800 means IPv4, which is interesting that the frame header is telling you IPv4 when it should probably be the IP header. But anyway, the IP header also tells you it's IPv4, and then there's all this other there's all these other things. I'm not going to go into each one of them. I could if we want, but it's not very important for the scope of this talk. But then here you have your source IP address and your destination IP address, and then you have your TCP header with your source and destination ports, and then the entire rest of this packet is your TCP payload or the data section. So this was me requesting a page on a quick little website that I wrote up for a demo that we're going to see later. But in essence, there's a whole lot of data with a little bit of management material at the top, and that's packet. All right, that's end of section 1. Any questions? All right, so this one's kind of more into the browsing question of, what happens when I go to a website on the internet. So I chose my company's URL and one of the pages that they host. So this is a URL. Most people know what a URL is, but they might not know how it's deciphered. So the first thing that's done is we look at the domain name or the fully qualified domain name. We reach out first to resolve that to an IP address. And then the next part is the protocol, which in this case is HTTPS. That's how we're going to connect to this IP address. And then finally, we're going to request the results of this script that's run. This capabilities.php is not a website. It's not. It's a script that's run on the remote end, and then the results are carried back to you to be rendered in your browser. So we're going to talk more about some of the technologies that they're used instead of just raw HTML. But So this is the order. It's where am I going? How do I connect there? And then what am I doing once I get there? So the first thing is DNS, and everything is hierarchical and also backwards. So the dot is something that you don't see because it's implied that it's there. This is the root domain. After that, you have com, and then disruptive-sol, and then www. So you have your root domain, your top-level domain, your domain, and then either a subdomain or a host name. And that's the same thing that I just said. So there's a couple different record types. These are probably the most important ones, but there's lots more. And then DNS works on UDP 53 or TCP for zone transfers or large transfers. HTTP, I'm not going to go into HTTPS because it's the same thing but with SSL wrapped around it. The underlying protocol is you're still doing an HTTP GET request. You just negotiate it on keys first. So HTTP gets and posts. There's others, but not going to go into them. You have various status codes. Those are probably the most two common. Page not found and OK, but you'll never see the OK unless you get the developer tools open on your browser. And HTTP is used to facilitate web pages, among other things. And again, here's some stuff that is used to generate those web pages dynamically, because pages should be dynamic. There's a big difference if you're ever doing web development between these three things: server-side code, client-side code, and the various markup languages that are used. When I first became a software developer, one of the easiest things to make is a web page. I guess it's the easiest thing to get instant gratification on, and it took me a while to beat into my head that you can't update something from the server with JavaScript unless you make another call to it with Ajax or something. So it's a tough lesson to learn when you're a newbie, but. So after that is TCP. So again, we're kind of working down the stack in order. So it's a stateful protocol. There's you're either connected or you're not, or you're half open, or you're closed. So we talked about sequence numbers and we talked about ports. So we're going to move on. UDP connection list. I mean, we've been over some of this stuff already because I got ahead, but. This is incorrect. I needed to edit that. The UDP layer only deals with ports. The IP layer is the layer that deals with IPs. And here we are at IP layer. So the formatting got a little bit off, but that's okay. It's just how IP addresses are represented in binary. When you're doing subnetting, it's important to understand, network, first usable, last usable, and broadcast. These are important things to know, but anything further and doing subnetting like by hand is not necessary for this talk, or at all, I guess. Nobody wants to subnet by hand. So IP routing, this is kind of where we get into the meat and potatoes of the internet. So these four things are probably the most common routing protocols used. RIP, I can't remember off the top of my head what it stands for. I don't know, but it uses hop counts. So like we talked about, routers are a layer 3 device. So it counts how many hops are in between you and the destination subnet. And it uses that information to figure out what the best way to get to that network is. So that's a very old protocol, and we have since decided that other things make more sense. OSPF, or Open Shortest Path First, is another one that basically uses path cost. So routes in between routers or layer 3 devices are measured in what's called a metric. And if you have a metric of 1, that's your cost of 1. If you have a metric of, say 15, well then your path cost is 15. What this doesn't take into account is, let's say you have a metric of 1, as route A, but then on the other side of that route A is, a very high latency link, like maybe it's a sat hop. And then next door you might have a metric of 2, and then beyond, him is a metric of 1. So it's important to know that OSPF isn't the greatest solution, because you can easily get stuck behind high latency networks, and then that's where we move on to EIGRP, which takes into account a lot of different variables to make very smart routing decisions. So bandwidth of the link, load of the link, delay, reliability, and maximum transmission unit. So those are all internal gateway protocols. They're used to operate inside of an autonomous system, which we're going to talk about later. And then BGP is what's used to inform other autonomous systems about each other. So like, ISPs there's not just one of them. So they need to know about each other, and they need to know which networks each other is capable of routing to. So BGP kind of uses some of the same metrics as EIGRP, but a lot of times it's much more based on the administrator and what the administrator chooses. So network policies and rule sets, as opposed to all these nice automatic things that could be done for us. BGP is usually automatically exchanged between autonomous systems, but as we're going to find out in a later slide, there's been a lot of BGP hijacking in recent years that is kind of shady. And then I had nowhere else to put NAT and PAT and bridging, so I put it here because it kind of made sense. So a while ago we were really worried about the fact that we were going to run out of IPv4 addresses, and we were worried that the internet was going to shut down if that happened. But I would venture to guess that if all of you went home tonight, well, not all, but most of you went home tonight, you guys are probably going to look at your computers and have probably very similar addresses. You're all probably in a 192.168.0 or 172.16. But you can still talk to the internet even though you have very similar or the same IP addresses, and that's accomplished through network address translation, port address translation, or port address translation is also known as NAT overloading in the Cisco world. And that's because instead of using a pool of IP addresses to go out and communicate one session at a time on your behalf, it's using port mapping. So when you reach out to the internet, you have a source port, and the router that's doing the port address translation for you remembers that source port. So when a packet comes back on that source port, it knows that I need to redirect that traffic to my internal endpoint that made that request earlier. And then bridging is used to merge or to join two physically different networks together. So going down one more level, we have ARP. And ARP is important because, as we talked about, we need to associate IP addresses and MAC addresses so that we can talk at the physical layer. So we talked about collision domains already, and hubs and switches. We didn't really talk about broadcasts, which is how ARP works. So when I'm looking for an ARP, or when I'm looking for a MAC address, I don't know where that lives. My switch might know, but I don't. So I send out a request on my broadcast address, and I'm looking for, an ARP request is literally, I'm looking for this IP address, who has it? And the response is, I have this IP address, here's my physical address. And then communication happens. So something we're going to talk about a little bit later is reverse ARP, or gratuitous ARP, which is a nice feature that's not really used in real-world networks, and it's also a significant vulnerability in the protocol. I can't think, in all my experience, I haven't seen a legitimate use for reverse ARP. But I'm probably not correct in assuming that there's no legitimate use for it. Basically, the way that works is I can tell you, I know you didn't ask for my address, but here's my physical address, and I'm at this IP address. So it's a way of informing you before you ask, I guess. But we're gonna talk about why this is a problem in a future slide. So finally, after that, you have bits on a wire, and it was really difficult to find a picture that actually talked about voltages on an Ethernet cable. But here we have it. I'm not an electrician, but electrons happen on a copper wire, and then you have a connection. Any questions on that one? That's probably one of my favorite interview questions to ask. So if you can speak well on how the internet works, and you're interviewing for a company like mine, or a company like any technology company that's gonna have DevOps or security or anything, they're gonna ask a question similar to that, and they're gonna expect you to know a lot of different things at a lot of different layers in order to pass that interview. So here we are, network service vulnerabilities. We're going to talk about an ARP poison. So that gratuitous ARP request that we were talking about earlier, and why that's a problem. So an ARP poison is a man-in-the-middle attack. You craft gratuitous ARP packets from the attacker to the victim, and it's a very noisy attack, so it's very easy to detect, but it's not always easy to prevent. And the end result is that it causes the victim to send all the traffic through the attacker. So the idea behind this is that most of the time you would ARP poison your victim to spoof yourself as the gateway. And that means that the victim is then going to pass all of its traffic to you, and you're then going to forward it out to the internet. But it's going to pass all the traffic to you thinking that you are the gateway. And this is a problem which sort of has been resolved by SSL, but it's still a problem for unencrypted protocols and unencrypted websites. So here's a video. If I just hit next, is it going to go? Okay. So here's my victim machine. It's a Windows 7. We're just going to show you the ARP table. The .2 box is my domain. Is my gateway. We need IP forwarding for this, because I need to then forward the traffic out to the internet so that the victim doesn't know he's being spoofed. So this is my Windows 7 IP address and the gateway, and the R just means spoof both directions so that the traffic coming back gets routed properly. So we noticed that the MAC address for the gateway has changed, which is not good, because now when I go to this super secure website that's not encrypted, that I didn't write in 10 minutes, and I log in with user123 and a bunch of dots, my connection is going to be sent through my attacker machine to, and then redirected all the way to the endpoint. So here we're going to stop the attack. This tool is nice enough to re-ARP everything and kind of restore everyone's ARP table to where it should be. And then while I was running this attack, well, I guess we're going to go back and look at the cleaned up ARP table. So you notice that, again, it changed back to its original state. So I was running Wireshark while I did that. And I'm going to open up this TCP session, or this web session, and I've got a slide that'll show you everything, but there is the post information for the username and the password in plain text that I logged in with. So this was a really big problem before SSL was a thing, or I should say SSL was a widely used thing. I want to say like Facebook and MySpace didn't use SSL until like 2005 or 6. So there's my super secret password. But yeah, even though this was posted to a website that I may or may not control, the fact that the traffic went through my box, my attacker machine, let me view everything, and because it wasn't encrypted in SSL, I get everything in plain text. So this doesn't work for only websites. This will work for literally any protocol that operates in plain text. So, use encryption. It's a pain, but use it. All right, so DNS attacks. Similar to ARP poisoning, but not really the same. There's kind of two ways to go about a DNS attack. There's a man on the side and a man in the middle attack. And a man on the side attack usually takes advantage of network latency. So I guess the idea is that if I'm sitting next to your DNS server and I watch a request go out, for Facebook, if I can see that request and then send you back a response and spoof the IP addresses and say, hey, Facebook's at this IP address, your server is going to accept that because it's the first one back. And then it's going to inform you, the user or the browser, that of the fake IP address of Facebook, and you're going to browse to it. And if I'm a good attacker and I've done my homework, I'm going to make a page that's pretty close to what Facebook's page looks like, and hopefully get you to log in or log into your account and give me your credentials. So more of the man in the middle attack would be kind of these denial of service attacks down here, the DNS flood and DNS amplification. With the man on the side, you're looking at this first one here with cache poisoning, or you could be an infected DNS server serving false DNS records. So a little bit about DNS flooding. If a botnet didn't want a DNS server to be online anymore, it would just send lots of requests at that DNS server, or they could use reflection, which is this amplification attack, where as an attacker, I can send a lot of very small requests for information, but then spoof the originator IP or the source IP address so that when the DNS server responds to it, it's going to my victim machine. And why this is important is usually my request is a lot smaller in size than the response, especially if I've figured out a way to get you to dump out a huge list of your entire domain or a zone transfer or something like that. I can with very small effort turn that effort into a very large effort and bring down your network or your box or whatever. But that's an amplification attack, and you can do amplification attacks with more than just DNS. We're going to talk about, I think 2 or 3 slides from now, we're going to talk about the GitHub denial of service that happened last week. So replay attacks, you don't really see these too much anymore because people are getting smarter with their crypto. But this is another man-in-the-middle attack, and the idea is that if I'm positioned somewhere between you and your endpoint and I intercept a bunch of traffic, the whole premise behind a replay attack is then I can take all of those packets, put them back on the wire, and I'm going to get the same responses from your server. So that might mean that if I capture a login session between you and one of your users, if I put those same packets on the network, I might get a valid session back, and then be able to do horrible things to your user. So another way that replay attacks are used is to enumerate service behavior. If you've got a web application that's sitting on the network and I don't know what it does, I might try to figure out what it does by trying to replay some sessions or some packets that have happened in the past. One of the biggest ways that replay attacks is used is to crack WEP. WEP uses a time-based initialization vector. So that's fancy lingo for how do I seed my hashing algorithm. So with using a replay attack, I can get your access point to basically spit out a bunch of these challenge packets, and with enough of them, I can crack your web password. So if I can figure out if I can inject packets into your network and deauthorize a currently associated base station, that I can then capture that reassociation and then replay that reassociation and get your access point to bleed enough initialization vectors that I can then figure out the actual key, and then I can attach myself to your wireless network as anybody else would. So we kind of also talked about impersonating a user or a system. But the important thing to note about a replay attack is it's pretty easy to detect and it's pretty easy to mitigate. If you use any modern crypto suite, like anything with a Diffie-Hellman exchange or anything with something that's not predictable, like time is very predictable. So maybe don't use time, or use time and something else. But like I said, it's pretty easy to detect and mitigate with a little bit of thought. So BGP hijacking. So this is something that's kind of happened a lot, and most people don't know about this. So we talked a little bit about BGP earlier, and the fact that, like a lot of these protocols like DNS and ARP, there's not really a lot of authentication or validation that happens. You can just send some stuff on the wire and people will trust you, which is not great. So April 2017, Rostelecom, which is a large Russian ISP, either accidentally or intentionally started originating 50 prefixes that belong to MasterCard and Visa. So I think this attack or accident lasted for like 30 minutes or something. But it's reasonable to assume that for 30 minutes, most of the world's Visa and MasterCard traffic was going through Russia. That didn't happen too long ago. December was 3 or 4 months ago. Google, Apple, Facebook, Microsoft, and a bunch of others were announced by Russian DV-Link autonomous system. So this attack happened twice in the same day for about 4 minutes apiece. So for a total of 8 minutes in December 2017, there was a whole lot of traffic from a whole lot of very commonly used services that was going through Russia. Again, I don't know if it was malicious or not. The word's still out, but it's, China's done it accidentally or not. A lot of people have done it. It's important that we acknowledge that it can be accidental because humans make accidents. And then networking-based denial of services. Yes. So I'm pretty sure the Visa and MasterCard stuff was not necessarily transactions, but not necessarily not transactions. It was the actual IP space owned by Visa and MasterCard were being routed through it. So it would be reasonable to assume that means transactions, but for example, like card processors are not necessarily Visa and MasterCard. So, it could be inter-account transactions that were redirected through, or it could have been, it really could have been anything because a card processor talks to the Visa card. So, anything to or from or through Visa and MasterCard was briefly going through Russia. Yes?
It's built on trust, right? So, when, for example, that technology, ISPs accept whoever announces if someone announces a route, ISPs pretty much accept those, that's legitimate. Is that the way you tackle it?
It's not really built on trust. So it's built on kind of the same principle as ARP, right? So a network is a very dynamic thing. A lot of it's not static. It was never designed to be static. So the idea behind BGP is that if stuff changes, let's say for example, Comcast buys a huge block of IP addresses. They need a quick and easy way to tell the rest of the world that they're responsible for routing traffic to those IP addresses. So there are, like I point out here, there are authentication and validations, but not really anyone's using them. And the other thing that's important is WINS isn't an ISP. Like you guys don't do a lot of, I guess, yeah. You guys aren't an ISP. Like you guys use someone else. Oh, okay. All right, well, today I learned. Okay. Yeah, so I mean, anything that's considered an autonomous system. So if you have a block of IP addresses or an IP address registered to IANA, you could be responsible for updating the rest of the internet with what you can handle as far as routing. And the internet right now is using a lot of BGP. So, any other questions on BGP? No? All right. So network-based denial of services. These are kind of a thing that have been around for a long time. Basically, I'm going to try to hammer your host with enough traffic or enough things to make it crumble. So HTTP post is up there because you can put a lot of information in an HTTP post request. And that server has to chew on all of it. So if you have a botnet and all of your zombies in your botnet send the same HTTP post request to a server, the server has to chew on that much data times however many bots you have in your network. Another commonly used thing today is IP spoofing. So you have, broadcast storm, Smurf attack. In a Smurf attack, it sounds cute and funny, but really all it means is that you changed the source IP address of the packet so that in the example of a DNS reflection attack, that's an example of a Smurf attack. I'm sending a packet to a DNS server with a spoofed source address, so that when the DNS server responds, it goes to a different IP address than the person that originated the attack. So if I'm attacking a DNS server, and I want it to then turn around and attack Kevin, I could do that, and that's an example of a Smurf attack. So Smurf attacks and reflection attacks are very similar, but the idea behind a reflection attack is that the request levied on your reflector is much smaller than the response, so that as an attacker, you can make much more requests much faster, and then just have a constant hailstorm of information hitting your actual intended victim. A SYN flood is another example, and this takes advantage of the fact that, so TCP, like we talked about, is a connection-oriented protocol. So the three-way handshake is a synchronize or a SYN-ACK, or a synchronize, acknowledge, and then an ACK. So a SYN flood creates, a bunch of half-open connections, which could exhaust all of the ports or file descriptors that a server can listen on. Which could effectively bring it down. With load balancing, you kind of sort of eliminate that, but most servers these days are smart enough to realize when they're being SYN flooded, and they'll just start dropping off the connections. All right, so here's the thing that I was talking about that happened last week. GitHub got DDoSed big time. This number probably isn't huge to most people, but it should be huge. So to kind of put this number in context, there's a little under 500,000 movies acknowledged by IMDb. We all know what IMDb is, yeah. There's a little under 500,000 movies across the world that IMDb has said this is a movie that has happened. So assuming that all of these movies are, HD quality, they're about 1.5 gigs in size. With the duration of the attack, so this attack happened for about 20 minutes, give or take, and this is how much data went through a second. So what that means is, over that 20 minutes, you could have downloaded a third of that 500,000 movies in 20 minutes. That's an enormous amount of traffic. And it's currently the record, but it's an upward trend, and every new DDoS that's of this scale breaks the record, and goes for next gold. So I was talking to some of you about kind of the mechanism behind this attack. So a lot of cloud hosting services like Akamai, Cloudflare's another big one. They're using these memcached servers that basically they're a middleman between you and the actual content provider. So if you've ever done networking with cable television, they have something called a content delivery network, or a CDN. And that's sort of what these are. Well, actually, it is what these are. So the responsibility of a memcache server is that it sits between you and the actual content provider. And let's say that content provider, normally gets 100 hits a second, or 1,000 hits a second. Well, it doesn't make sense for the content provider server to process the same request 1,000 times. So what happens is, 1,000 people will hit this content delivery network, and then, so the first one there usually gets the actual request. So the request will actually go through to the content provider, and then the results come back and they go to the requester, but they also get cached at this CDN site. So the remaining 999 requesters of that same page get a cached version or similar, and that really speeds up the internet, and it takes a huge burden of networking, processing, all of the above off of the content provider. So these are all over the world. And they're a great help, but so when they're not secured right, they can be used as tools of reflection attacks. So in this instance, there was a whole bunch of them that were accepting requests from, or cache update requests from anyone on the internet, and someone figured this out and decided to basically Smurf attack using these as their reflectors, and they would create lots of small requests that would then reflect and turn around huge results and sent to the GitHub servers. So Akamai is also a company that does DDoS protection, and they figured out what was happening in like 8 minutes or something. And then they mitigated it and started blocking the IP addresses, and they're trying to figure out who done it. But that's kind of how that GitHub attack happened. Any questions on that one? You can. Usually, it's more about costing your victim money. So in the case of GitHub, GitHub went down for 10 or 15 minutes, but I don't really know how much money they lost in 10 or 15 minutes. When it's happened in the past, it's been against, there's been, attacks against Wells Fargo. I think last year, year before, Wells Fargo was hit by a huge denial of service, which at the time set a record. So when you're talking about a bank, your impact could be millions, billions of dollars. I don't know. But yeah, it's sometimes a retribution attack. It's about costing your victim money. At the end of the day, there's unless you're a direct competitor, and maybe the incident caused some of your customers to switch over, I don't think it would really benefit the attacker. But it's about costing your victim money. All right, so no more questions on attacks. No? Okay. We're going to quickly go through defense. Oh, I'm doing all right on time. Quickly go through defense. So if you're a network guy, if you're a security guy or gal, you've heard of DMZ before. The idea behind DMZ is that you put all your vulnerable services in their own bubble on your network, and then you have routers and firewalls between the internet and your DMZ, and then your DMZ and your intranet. This is to protect, your expensive data, your proprietary secrets, your users that might be in here from someone who might have owned, your DNS box or, your mailbox. Unfortunately, the trend has now become to attack all your users here with spear phishing campaigns, and doing DNS cache poisoning might affect this box, but it defeats the whole purpose of DMZ, because at the end of the day, your intranet users are going to use the poisoned cache to get out to a fake website, and it's game over. So this is still a smart thing to do. It stops a lot of attacks, but it certainly doesn't stop them all. It's all about, security is all about layers these days. Some of the things you'd want to do when setting up your network, a lot of these things are usually architecturally a good idea too, but they also bring some security benefit with them. So variable length subnet masking basically says I'm going to build my subnet to account only for the machines that I need. So if you've got 100 machines in your network, you might want to only make sure that 128 can be attached to that network at any given time. So this speeds up routing, but also can prevent some attacks. Make sure you're doing out-of-band administration. You shouldn't be SSHing around a production network to administer servers. You should be using the back end that's ideally on a separate VLAN, which is the next item, ideally connected only to machines that administrators have access to, et cetera, et cetera, et cetera. So VLANing is the concept of creating multiple subnet or multiple LANs that use common equipment. So it's a per port feature, so you can have, if you have a 48 port switch, you can have a different VLAN on each port, and each of those ports then has to be routed between each other by a router or the switch itself if it's a layer 3 switch. And this helps segregate and trunk and keep all your network or all your traffic separated. So you can have, if you're a small business and you can afford only one switch, or you're doing some sort of VPNing, you can have different VLANs across different areas, but still have the network separated from each other. So routers and firewalls, kind of, we talked about these already, but they keep networks separate in the case of routers, and they keep bad things out in the case of firewalls. Or they keep bad things from leaving as well sometimes. IDS and IPS, I think was a previous talk, 2 talks ago, so I'm not going to talk about those a lot. But intrusion detection system and intrusion prevention system usually sit on your exterior and watch for traffic and react to traffic if it detects or thinks it's an attack. And then the last thing I'll mention about network layout is use passive taps. Look at traffic. It's a pain in the butt, but passive network taps is probably one of the best ways to get a non-discriminate look at what's happening in your network. Physical security is pretty much everything that you'd probably think about if you'd think physical security. These are things that you can control that don't live in cyberspace, with the exception of cameras that might be going over your network, which again should be out of band of your production network. So physical access to systems. Don't leave your wiring closets unlocked. Disable unused ports. Don't have exposed USB ports. Don't leave your cables exposed. Believe it or not, people can actually put a tap around an Ethernet cable to get the electromagnetic emanations off of the twisted pairs. It's a thing that's been done. There's another thing called Tempest, which is your keyboard actually each key gives off a unique electromagnetic signature, and you can actually pick off what keys are being pressed, and you don't even have to be in the same room. So don't leave electronics exposed at the end of the day, not just cables, just electronics. Keep your password safe, and don't be dumb with wireless. Wireless should never be on the same subnet or network as your as anything that's. At the end of the day, you should treat wireless as a perfectly wide open attack network or attack vector. It should never be adjacent to anything that you hold dearly, because it's not secure. Period. And then this is just some CISSP things that I thought might be interesting to someone. Defense against downtime, use battery backups, have hot and cold spares. Notice that backup strategy and RAID are two different bullets because they're not the same thing. Don't let anyone tell you that RAID is backup. It's not. RAID is a good idea to get a lot more out of a couple disks, and it should never be used as a backup strategy. And then finally, load balancing. Again, if site A goes down because of an earthquake, you should have site B with some hot or cold spares ready to spin up at a moment's notice. And then some more of the same things. These are some of the systems that you might see in a data center. There's like 4 different kinds of fire sprinklers, charged line. I don't remember the rest, but there's charged line and there's like empty line, and it all determines whether or not there's water in the sprinkler systems or not. Because water and electronics don't mix. As some people probably know. Halon is interesting. Halon is an inert gas that kills humans. But it puts out fires because fires can't breathe halon. And then, automated shutdowns and load balancing to protect equipment in the event that equipment can be recovered after your emergency. So I went a lot farther, a lot longer than I thought I would, but hopefully you guys don't feel like this guy. Are there any questions for me about anything that we've talked about? No questions. All right. We're all networking experts here now.